In this lecture, we introduce the hyperbolic orbits. We describe how they look like, which parameters are defining such an orbit, evidencing the differences with elliptic ones. Moreover, as done in the previous chapter, we will link the position with the time. Let's remember once again the trajectory equation that we have found in the first lecture. This equation is valid for any orbit type, both elliptic and hyperbolic. If hyperbolic, then the eccentricity E is greater than 1. We want now to display the meaning of the geometrical parameters of the conic: A, B, E, RP, and RA. A is the major semiaxis, metered from the center of the conic to the periapsis, from this position to this position. In case of the hyperbola, this value is negative because the center of the conic lays on the right side of the periapsis. The hyperbola actually has two branches, but we consider the one on the left side for analogy with the ellipse. The right side has no physical meaning. We display both here just for practical reason, for easy reading of the symbols. B is the minor semiaxis and represents the distance of the focus from the asymptote, actually this distance. C is the distance of the focus from the conic center, also negative. RP and RA are respectively the radius of the periapsis and apoapsis, and both are positive. Now we want to link the angle theta with the time. Since the hyperbolic orbit is not repeating, we cannot define a period, even though we can still say the areolar speed is constant. Like for the ellipse, we define a fictitious anomaly called hyperbolic anomaly h. This is not an angle, however. We can demonstrate such a relationship between the radius and the hyperbolic anomaly h. This formula is very similar to the one that we have found for the ellipse, using capital H in place of capital E and hyperbolic cosine in place of trigonometric cosine. Moreover, it does exist a relationship between the hyperbolic anomaly and the time that is formally similar to the Kepler equation of the elliptic orbit that we write here below. The differences are three. It appears the hyperbolic sign in place of the trigonometric one, then the left-hand side as opposite sign, and the argument of square root as a negative sign, so that its value is positive. We remember that A is negative for the hyperbola. Finally, theta is found by a similar tangent formula as per the elliptic orbit, but with the hyperbolic tangent on the right-hand side. Moreover, the denominator inside the square root has opposite sign, so that the whole argument is positive. We remember that E is greater than 1. We need to take a break here and introduce a new argument, since it is needed for the following development. We tell about the energy conservation by the orbits. The mechanical energy of an orbit is the sum of the kinetic and the potential one. The kinetic energy is well known, being half of v square. Since we refer to the unitary mass, the mass is not taking place here. The potential energy, capital V, is minus m over r. The potential energy, for definition, is a function whose derivative with a negative sign is equal to the force. That's it. Since the energy is not changing along the orbit, we can write it at the periapsis, where r is rp. And now, because the angular momentum h is constant, we can calculate it at the periapsis also, finding h equals rp times vp, because at the periapsis velocity and radius are square. But h is also equal to the square root of m times p, and rp we can get from the trajectory equation is equal to p over 1 plus e. Finally, in the kinetic energy, we can write h over rp square in place of v square. and it turns to this expression by replacing the trajectory equation. Likewise, we can express the potential energy as function of P and E. If we sum them together, we get, for the mechanical energy, this expression. And remembering that P is A times 1 minus E squared, we get a very simple formula: mechanical energy equals negative m over 2A. And this is valid for any orbit. The unit is joule per kilogram, that is equal to square meter over second square. From the energy conservation law, we can isolate the velocity and get this expression in red. It represents the velocity modulus of an orbit with a given semiaxis A at a distance r from the central body. Important result is that the velocity for a given distance depends only upon the semiaxis. That means, for example, that a small body along the three orbits represented in green, orange and purple respectively cannot have same velocity. In order to have same velocity, the orbits should have same semiaxis. The elliptic orange orbit displayed in the picture has equal semiaxis of the orange circle, but the orbit is impossible because the central body is not occupying the focus. This is contradicting the first Kepler law. The only possibility to run such an orbit is that its apsidal line is rotated like in the picture. In this case, the velocity modulus can be the same, but the two velocities have different angles. Let's see now an application for the orbit determination. We want to run a similar problem as seen in the previous lecture, but using a different procedure. We keep the same distance r, 20,000 kilometers, but we change the velocity vector. Now it is 3 and 8 km per second respectively. Our task is to find A, E and theta 0 as per the previous problem. From the first Binet formula we get the angular momentum h, that is 160,000 square kilometer per second. And now we find the velocity modulus square, that is 73 square kilometers over square seconds. From the vis viva equation, solved for the semiaxis A, we obtain A equals negative 12,028 kilometers. Since A is negative, we recognize soon that the orbit is an hyperbola. Then we can get P, that is h squared over m, and the eccentricity from the square root of 1 minus P over A. That turns into 2.518. The only missing info is the angle theta 0. We use the trajectory equation solved for theta 0. By means of the inverse cosine function, we get 28.6 degrees. But because of the ambiguity of the cosine function, we need a separate verification. If VR is positive, then the angle is positive, otherwise is negative. In this case, VR is positive, also the angle is correct. In the video comments, you will find also a link to the GeoGebra application, where the orbit is well represented. Coming back to our hyperbola, we need here to couple its geometrical parameters with the kinematic data of the body. If we apply the energy conservation law at infinite distance from the focus, we get 1/2 V infinite square equals minus m over 2A. That makes A equals negative m over V infinite square. The semi-angle phi infinite between the asymptotes we can write as cosine phi infinite equals A over C. But C is equal to A times E. Also, cosine phi infinite equals 1 over E. The minor semiaxis B we can express as negative A times square root of E squared minus 1. The deviation angle delta is pi minus 2 times phi infinite. Therefore, cosine phi is equal to sine of delta half. And since Rp is A times 1 minus E, that is the periapsis, then 1 over A turns into A over A minus Rp. And by replacing the value of A found above, we get this expression. Sinus of delta half, that is the deviation angle, is equal to me over me plus Rp into V infinite square. Let's see here how the orbits look like as A and E vary. We make a graphical representation of the trajectory equation by means of the program GeoGebra. First, we keep A constant and we change E from 0, circular orbit, to 3, hyperbolic. Then we keep E constant and we change A from -5 to -1 within the hyperbolic range. To conclude our presentation, we run here two exercises, the first for an elliptical orbit and the second for hyperbolic one. Given is the semiaxis A, the eccentricity E, and we need to find R and V when the elapsed time is 3 hours from the periapsis passage. First, we calculate the mean motion n. Using the me of the planet, we assume the Earth, and the known measured semiaxis. The mean anomaly, capital M, is defined as n times t. Also, n we have found and t is given in the data of the problem. We get 2.132 radians. From the Kepler equation, we get the eccentric anomaly capital E using a numerical method. For the guess value of capital E, we get the found M. Eventually, E turns into 2.361 radians. From E, we find theta using the tangent formula, and theta turns into 147,3 degrees. After determination of P, from the trajectory equation, we get R, that is 26,716 kilometers. Finally, with the vis-viva equation, modulus of the velocity is 3.387 km per second. We notice that in this problem, only the modulus of the velocity and the radius are requested. The second exercise is a little different. Here are given the measured semiaxis A and the eccentricity E. Moreover, for t equals 0, the radius r1 is known. The task is to find the delta time for reaching the radius r2 greater than r1 after periapsis passage. We go finding first the hyperbolic anomaly capital H by using the trajectory equation as function of capital H. We notice that while inverting the hyperbolic cosine, we have the ambiguity of the sign, as per the trigonometric function. But since we know that one radius is before and the other is after the periapsis, then the two anomalies must have opposite sign. However, we take the positive value for both, since we know in advance that the corresponding times needs being added. The values are for capital H1 and capital H2 displayed here. Then we calculate the mean motion n, and by using the Kepler equation, where all the remaining data are known, we find the mean anomaly capital M1 and capital M2. By dividing those anomalies by the mean motion, we find eventually the times T1 and T2. They are both positive and they need to be added. The total delta T is 2,877 seconds. That is all for today. Thanks for your attention and see you next time. Bye bye.